we are now trained at solving inverse problems. And one of the inverse problems that I would like you to look at, or at least I would like you to look at one fundamental problem that we started with, the problem of sampling, of how do we sense an image, how do we sense a signal in general, how do we perform this analog to digital conversion. I would like you to rethink this problem in terms of solving an inverse problem. And it makes sense, right? Basically, we have some latent object that we would like to measure. We obtain a discrete set of measurements because this is the only thing you can represent by a digital computer. So you're obtaining a discrete, typically a finite set of measurements, and then you need to reconstruct that object back. And ideally, you would like also to say some theoretical statements when this reconstruction is possible and how accurate it will be and how sensitive it will be to noise, so make some statements about stability. But this is exactly what inverse problems are about. You have some measurement system, and you would like to invert its action. Okay, so let's rethink in this optics. Let's rethink the entire problem of sensing and sampling, and you will see that first of all we'll be able to explain what we did until now when we talked about sampling on lattices from this perspective. Then we will be able to generalize it and generalize it to way beyond what we thought we could do with just using Shannon Nyquist theorem. Okay. So this is just a cartoon of what we did with when we talked about sampling. We sampled a continuous domain function on some lattice L star. This was our definition for lattices L star. We obtained a discrete domain signal. Then we typically do some processing here. This is what DSP is about, or digital image processing is about. We are doing some potentially very complicated processing in the digital domain. We can do denoising, we can do some other manipulations on our image, and then we interpolate back on the same lattice, right? And of course, our assumption was that sampling here is done by multiplying by a periodized delta distribution, right? So we had this sampling with deltas, and we know that nothing in the real world works with an ideal delta. And then we had interpolation on the lattice, and we said that an ideal interpolation kernel is a sink. And we know that we cannot build sink in analog electronics. We cannot build it in optics. We don't have a sink. We have something else. And then basically, how does this impact our ability to faithfully reconstruct the signal? We didn't really talk about it. Okay. So basically, just to formalize what we had a continuous domain signal. We sampled it on some lattice. Let me bring you back to the canonical form. Basically, we are just sampling on the integer lattice. Then we did a coordinate transformation, and we can generalize this to any lattice. So let's just, for simplicity of the derivations, let's stick to the integer lattice. And then we obtain the discrete domain signal. This is how the samples in the discrete domain looked like. So I'm assuming that I really have this ability to measure a pointwise value of a function. Of course, this is meaningless when, for example, when you're counting photons in an imaging device. You cannot really have this instantaneous pointwise measure because you need to open some aperture to collect this rain of photons. If you just collect rain on a point that has no dimensions, you will be collecting zero drops of rain, right? So you need to open some area, and area means that this is not this ideal setting anymore. You have some integral with some aperture function. And then basically we had this very beautiful geometric sampling theorem that tells us if our function is band limited, meaning that if its Fourier transform belongs to this, basically if it is supported on this unit cube, or in general on the dual lattice, then we can reconstruct our function exactly from our measurements by doing this interpolation with the sinks. So this was our interpolation kernel, and this sampling theorem exists for probably 70 years, if not more. Can we do better now? Okay. So let me massage this model a little bit. So I will bring it to to our terms of inverse problems. So basically, what we have a prior. We can think of it as a subspace prior. We assume a priori that our signal belongs to a subspace of L squared. It's not any square integrable function. It is a function that can be written as a linear combination of these sinks, which is equivalent to saying that it is band limited, right? So basically, our subspace prior, in other words, tells us that we have a basis of integer translations of sinks, and our function belongs to that span. So it belongs to the subspace. It's a subspace of L squared. And our function belongs to that subspace. Okay, so it can be written as a superposition of these basis functions. What is nice is that these integer translates of sinks is an orthonormal basis, and you can check it easily. These are not easy integrals to compute, but you can go to a table of integrals and just evaluate the inner product. You can use the separability property of a sink. So if you do a one-dimensional integral of two integer translates of a one-dimensional sink, you will get that unless n is 0, they are basically their inner product is 0, and then you can use the tensor product property to generalize it to d dimensions. Okay, so basically, if this is the case, let's think of it in a different way. Let's construct a synthesis operator that takes a sequence with discrete indices into a function in L squared, and it will work like this. I give you a sequence of coefficients, C, and you are just going to take take C at every index n. N is a multi-index, the d-dimensional multi-index, and use it as a coefficient for the corresponding basis function phi n. And phi n, I remind you, this is just a translated sink. Okay. Now, let's see what happens if I first do an integer translation of this sequence by this operator tau m. What happens to the result? So if I do integer translation, basically it is by just putting n minus m instead of n in these coefficients. Let's just reindex the sum. So this makes C depend on this n prime. N prime, of course, equals to n minus m. And the plus m will pop up here, right? And again, let's just substitute what is written here. These are integer translates of this thing. So it's x minus n prime minus m, right? And I can write this as the translated version of the basis function phi n. And compactly, I can write this as the translation of the dictionary phi, of the synthesis operator phi, acting on C. So basically, we can see that this synthesis operator, is translation equivariant. It commutes with integer shifts. Okay? Nice property. What about the adjoint of this operator? We call the adjoints of synthesis operators, we call them analysis operators. So an analysis operator will take us from a function of a continuous variable to a discrete sequence, or basically a discrete image, sequence indexed by a multi-index, a d-dimensional multi-index. So let's just compute this adjoint formally. Let's take phi c. We take some c in L2 and some g in capital L2. Okay. Let's compute the inner product. I'm substituting the action of the dictionary explicitly here. It's the sum over C and phi n, inner product with G. Then let's use the linearity of the inner product. I'm taking the sum outside. I'm taking the C-ns outside. And what I have here are these inner products of phi n with G, inner products on capital L squared. Okay. Let's just flip the order of the arguments in this inner product, and you know that inner products are conjugate symmetric, right? So the complex conjugate will pop up when you reverse the order of the arguments. And now this sum, how does it look like? So you have a sum. Let's call this sequence, let's call it dn, adjoint. So you have a sum cn dn adjoint. This looks like an inner product on lowercase l squared. Okay, so this is the inner product with this sequence. So this sequence, basically, we took an operator phi here, and we removed it from the first argument, and we did something with the second argument. This something is called the adjoint operator of phi. So our adjoint, our analysis operator, is just the projection of phi onto the basis functions phi n. Okay, so this is the adjoint. And you can just think what happens when phi is a matrix. What is the adjoint? It's just the transpose, right? How do you compute the transpose? You compute the inner products with all the columns, right? So this is what you do when you transpose the matrix and multiply it by a vector from the right. You are computing this vector of inner products, this sequence of inner products with the columns of phi. Okay? So this is our analysis operator. Now what happens when we take a function that belongs to our space? So it is band limited. It is represented by these integer translates of sinks with some set of coefficients Cn. And let's apply our analysis operator to this function f. As the result, we are going to get a set of coefficients. And let's guess what coefficients are you going to obtain. I'm claiming that you're going to obtain exactly the coefficients C. Okay, and this is because of orthonormality of the original operator phi. Let's just do it quickly. I'm applying phi to this form of the function f, again using linearity of the operator. This will be a superposition of phi adjoint acting on phi n, the basis function phi n. Let's now substitute explicitly the form of the adjoint, right? This is this sequence of the projections of, now it will be phi n on phi m, and we know that the phi's are orthonormal, right? So the only thing that will survive will be the cases where m equals n, right? That's why I'm writing this delta sequence here. And as a result, I'm going to get Cm. So exactly the same coefficients that I started with. And again, this is the product of orthonormality of our basis. Now let's evaluate. Let's use the fact that sinks have zero crossings at integer points of the lattice except the 0 point. So basically, this phi n m, when I'm substituting an integer, a vector, as the argument, I will be getting zeros except the 0 vector. And let's evaluate this fm, this f, or this function f at point m. Okay, so I'm substituting again this integer argument into the basis functions. So again, m is on the integer lattice. I'm going to get this, right? Because of the 0 crossings of the sink. And this is Cm. Okay? So I started with a function that is represented as this linear combination of the shifted sinks. And when I evaluate it at an integer point, then basically only one of the coefficients lives and the rest are dead. The rest vanish. They are set to 0. So essentially it means that the values of the function at point n are the coefficients, the corresponding coefficients at the corresponding n of the analysis operator. Or let's think of it in the other way. What the analysis operator gives us are the pointwise samples of our continuous variable function on the integer lattice. So essentially, this analysis operator does the sampling. Okay? Again, so now we have two operators. The analysis operator, we just saw that the application of the analysis operator is like this product with the delta, with the Dirac's bed, that periodized delta distribution. It does the sampling, and the synthesis operator does the interpolation, right? So again, we have sampling by the analysis operator and interpolation by the synthesis operator. And the sampling theorem essentially tells us that if our function is band limited, then applying the sampling, the analysis operator, and then the interpolation, the synthesis operator is just an identity map. Okay? So the function is reconstructed perfectly. If it is not, so let me draw a geometric interpretation. This is the space of band-limited functions. Of course, it is an infinitely dimensional space, but I'm given only a two-dimensional screen, so pardon me this limitation. If my function lives here, the projection, this orthogonal projection, phi adjoint phi, keeps me within the same space. It will be the same vector. If my function is not band-limited, this is my function f, I'm going to orthogonally project it into this space. So this will be the outcome of the projection. So I'm not going to reconstruct my function exactly anymore. I will reconstruct a band-limited version of that function. Okay? This will be my projection. Any questions? So now I can also be a little bit fancier. I can think of sampling as an inverse problem. So again, I can write this forward model, my observation. Let's assume that I'm thinking of my function belonging to some subspace plus some additive zero mean white Gaussian noise. My prior is that f belongs to the space of band-limited signals, which means that it can be represented by this basically by this set of coefficients on which the synthesis operator works. I will not assume anything regarding my C. I have no prior on C, which means that I'm assuming essentially a uniform prior on these coefficients. And as a result, I will have this negative log posterior, which is exactly equal to the negative log likelihood in this case, because I have a uniform prior, and it will look like this, right? And essentially, my map, or in this case also the ML estimator, will look like this. I'm estimating the set of coefficients C such that the synthesized function using these coefficients resembles my measurements Y as closely as possible in the Euclidean sense. I get these optimal coefficients, and then I synthesize my function using the synthesis operator phi. And of course, this problem has a closed form. This closed form is exactly phi adjoint Y. So this is an orthogonal projection onto the space of band-limited functions. So you can view it as the outcome of maximum likelihood or map estimation. Okay, so basically the classical sampling can be viewed as the solution of this inverse problem. Now, let's look at what happens in the real world. In the real world, nothing resembles our idealization. So images are not band-limited. Image is the worst. It's the worst possible assumption you can make that an image is band-limited. Of course, there is very low. You have the diffraction limit of a lens, which acts as a low-pass filter. So basically, you cannot go better than, let's say, half the wavelength of your light. But that is very far, or used to be very far, from the density of the pixels that you can create, at least for visible light. So basically, you are at the sampling rate that you typically have in imaging sensors. You're not limited by that band limitedness of the physically unsurmountable blur that every lens introduces. Today cameras have pitches that, let's say, go to 1 micron or even below 1 micron. So you are getting close. You are getting close to the band limitedness, basically to this diffraction limit of the lens. Still, this is not the limiting factor of most imaging devices today. So if you remove that blur that a lens introduces, essentially images have discontinuities because one object in the scene has a boundary, and then below it you have another object. So there is a discontinuity. The function is not even C0. It's not continuous, and the way it translates to the Fourier coefficient. So the basically localization is dual to continuity, to fast decaying higher order derivatives in the Fourier domain. So if you have if you don't have fast decaying higher order derivatives, because you don't have even higher order derivatives, it means that the Fourier transform is not localized. So it has very slowly decaying coefficients. So the energy is spread over high frequencies, and it means that the image is not band limited, or at least it has negligible energies at very high frequencies. The sampling is not ideal either. In typical imaging devices, we have integration. You need to collect light on some area. So it's not a delta, it's something else. You're sampling with maybe integer translates, because your array is usually regular. Of course, there are some optical variations that the rays come at different angles in different regions of the sensor. So it's not exactly not exactly shift invariant, but let's assume that it is shift invariant. But the point is that psi is not a sink. You're not sampling with deltas. You're not doing inner products with sinks. You're integrating with some other function. It doesn't have negative lobes, for example. And interpolation is not ideal. Show me a display that can implement a sink kernel. You cannot implement a sink kernel. First of all, because the sink has negative lobes. You cannot do negative intensity on a display. So again, basically all our assumptions on sampling, they simply do not hold in reality. They don't hold in the real world. So let's try now to take our perspective on sampling and represent this kind of real world system using, again, an analysis operator and a synthesis operator. They don't need to be the same. The way we collect photons doesn't need to be the way the LEDs in our OLED display project light. There might be super complicated technological considerations that even prevent them from being the same. These are not basically completely different technologies. One that collects light and one that displays light. So at the end, we end up with this product of this composition of operators, the sampling and the interpolation operators, that they simply don't yield an identity function, an identity map. Okay. So basically, if we just assume Shannon Nyquist sampling, it will be an approximation, and in real systems might be a very bad approximation. Okay. And my question is, can we do better? Now we have this more general view. Can we do better? What we can do? So let's assume that we have this translation equivariant sampling. We are projecting on two integer translates of some functions psi, or convolutions with psi mirrored, right? Basically, inner products is like convolution. I'm taking the sequence of convolutions of f with psi mirrored, psi bar. So psi bar, of course, in our notation is psi minus x, right? And I'm sampling the results of this convolution at the points of the integer lattice. And I'm a little bit sloppy here. I'm assuming that psi's are real valued. Otherwise, I need to put the adjoint somewhere, the complex conjugate. And I'm also given a translation equivariant interpolation operator. So I will take some sequence D of coefficients, and I will synthesize them with integer translates of these functions, of this function phi. Okay? So I can think of it as just modulating my D with the Dirac's bed and then convolving the result with this function phi. So this is my, if you think of a physical device, this is the envelope of light that, for example, a pixel in the display produces, or the shape of the dot of ink that a printer injects on paper, or whatever is your interpolation device. Okay? So basically, these are two given sampling and interpolation operators. I would like to make them as close as possible to Shannon-Nyquist operators, but in practice they are not. So basically, this psi is not a sink, and this phi is also not a sink. Okay? So what I'm going to do, I'm going to introduce a digital correction. So you see, I wrote here a different set of coefficients D. So I sampled some set of coefficients C. I sampled something using this non-ideal sampling. So I have an image that is not exactly point-wise values of my continuous, my analog signal. And then I'm going to do some manipulation, some digital manipulation on that image that I sampled, and then I will send it to my display. So basically, I have some system H that modifies my coefficients, and this is done entirely in the digital domain, and then I do the interpolation. So can you now characterize this correction operation that will result in an identity transformation from sampling to interpolation? Okay? So this is how I would like to approach this generalized sampling problem. So again, the setting is that we are given the analysis and the synthesis operator. So we are given an existing imperfect hardware on the analog to digital end and on the digital to analog end, and we would like to do some digital domain correction that makes them talk in the same language. Okay, so this is the goal. Okay, so again, a cartoon representation. We have a sampling operator. We have an interpolation operator. So basically here we have this wild analog world, right? And here we live in our nice and easy or easier digital world. Okay? And we would like to bridge between these two imperfect pieces of hardware. So let's do a least squares solution. And this is not the only criterion, but let's just do a least squares solution. We would like to find, I remind you that we would like to find a system that H that satisfies this. Typically, it will be impossible to satisfy perfectly. Let's satisfy it in the least squares sense. Okay. So our estimated signal is phi d hat. D hat is the solution of this minimization problem. Okay. So you can call this map from the given input C, which is our sampled observation. Sampled observation is this psi hat f. Okay. I would like to find the set of coefficients d such that when I synthesize them with phi, they are as close as possible to f. And this is exactly what I'm writing here. I'm taking my d, my set of coefficients, I'm synthesizing them with phi, I am sampling them back using psi adjoint, using this sampling operator, and I would like to obtain my data C. And if I don't, I would like to minimize the discrepancy in the L2 sense. Okay? So this is a least squares solution. And this map from C to D is exactly the action of my system H, right? This is the map. I'm not saying that it is linear. I'm not saying anything about it. Okay, but you will see it will be linear. Of course, this problem has a closed form solution, right? This closed form solution is called the Penrose-Moore pseudo-inverse, which has this explicit form, right? If you just write the gradient of this L2 norm equated to 0, this is what you're going to get. Okay? I am a little bit sloppy here. I'm not telling you why this inverse exists at all, but this matrix is invertible. What is written inside the inverse is full rank, and this stems from properties of basis, basically of basis on these infinitely dimensional spaces. And of course, if you do it in a finitely dimensional space, these would be just matrices, and you will see that it will, for any basis, this will always hold. For infinitely dimensional spaces, we need to be a little bit more careful. Okay, so basically our system appears to be a linear system, right? So the pseudo-inverse of a linear operator is also a linear operator. It's linear. Okay? Let's evaluate. I would like now to look at what appears here inside the pseudo-inverse. Let's call this system G. So this is the action of the system G on the vector of coefficients C. And let's probe them at point M. Okay, this is a discrete domain system, of course, so M is an integer vector. Okay? Okay, so let's see what is happening. I'm first applying phi, and then I'm applying psi, right? So let's first apply the outermost operator, the psi adjoint, right? So the psi adjoint does does this, right? So I'm looking at the mth point. So a psi joint gives me a sequence, a discrete domain signal. So I'm looking at the mth coefficient, the mth element in that sequence that that psi joint gives me, and it looks like the argument, which is this phi c, inner product with the translated psi, translated to point m. Okay, this is how my analysis operator is defined. Let's now substitute this phi c. This is how phi c looks like, right? This is my synthesis operator. I'm synthesizing, I'm taking the superpositions of translated versions of phi with the weights Cn, okay? And of course, I will do our regular manipulations. You should be already trained to do it with closed eyes. I'm reversing this. I'm reversing the orders of the inner product and the sum. I'm taking the coefficients outside the inner product. And what I have here is an inner product of the translated phi and the translated psi. Phi translated by n, psi translated by m. Okay? So let's just, again, I'm calling this system G. This is not the pseudo-inverse. This is what appears in the parentheses of the pseudo-inverse. Okay? So this is my system. Let's spell out this inner product. This is, of course, an inner product on L squared, right? So this is an inner product on L squared. Let's change the variable in the integral. I would like to get rid of this n. So I'm integrating with respect to this new variable. Of course, the differential form keeps the same volume. I'm just shifting, translating the variable. So basically, I have an inner product between phi and, so integral of phi and psi joint at this point plus n minus m. It looks like, almost looks like convolution, right? So I can write convolution. It would be convolution if x came with a minus sign, right? So I'm doing our regular trick. I am mirroring the argument of the function, and then it looks like convolution. So I have convolution of phi with psi adjoint mirrored, and if I'm assuming that my sampling functions, typically in imaging, it would be real valued, so I don't care about the complex conjugate. It's the convolution of these two functions of the sampling and the interpolating kernels evaluated at point m minus n. And I'm summing the outcome of this convolution with these weights Cn. So this also looks like convolution. So this convolution was in the continuous domain, right? This is the convolution in the continuous domain. What is written here now, this sum is also a convolution. It's a discrete domain convolution. So let's just introduce this notation. I will call this a cross-correlation sequence. It's a deterministic version of cross-correlation of stochastic quantities that we had before. So a cross-correlation will be just convolution of one sequence with the mirrored other sequence. So this is basically, this is a continuous domain signal. Okay? It's a cross-correlation. It's basically a convolution of phi with a mirrored psi. Okay? And I need to add the complex conjugate if the functions are complex. So this is the cross correlation. I'm sampling it at integer points, and I'm essentially doing this discrete convolution with the sequence C. Okay, this is discrete convolution of sequence C evaluated at point M. Okay, so basically what I did, I sampled this continuous domain signal. I sampled it. And then I digitally convolved it with C. So again, this is a digital convolution. It's a discrete domain convolution. Okay? And again, this is my system G. So first of all, you can see that it is translation equivariant. It was linear, and it is translation equivariant. So essentially, this digital correction that bridges between one crappy a piece of hardware to another incompatible crappy piece of hardware is a filter. It's a digital filter. Okay. So let's see what happens in the frequency domain. I would like to characterize it in the frequency domain. If it is translation equivariant, I can write its Fourier transform. So let's compute the cross correlation. So this cross correlation, of course, will be just a product of two functions, right? So this mirroring will become the adjoint and the complex conjugate, and the complex conjugate will kill that complex conjugate. So essentially, this R phi psi at analog frequency psi is phi psi psi psi. Too many Greek letters here. So basically, this is how it will look in the analog frequency domain. In the digital frequency domain, we sampled that continuous domain sequence, right? So what sampling does, sampling periodizes it, okay? Oh, so this was already written, okay? So basically, I periodized that continuous domain Fourier transform, okay? And now I need to do a discrete domain convolution. So I already rewritten this in terms of this digital frequency omega. I on purpose selected the integer lattice, so I don't have any scaling coming from the lattice, right? So omega and psi are identically the same. So basically, I have this periodized Fourier transform. I'm now doing so convolution in the space domain. It means that I'm just doing product of C omega with this R. So essentially, it means that the frequency response of this system, so this is my impulse response, and the frequency response is given by this periodized correlation of the analog sampling and interpolation kernels, right? Now we wanted the pseudo-inverse, right? So the pseudo-inverse, for the impulse response, I cannot give you a nice expression in closed form for every case, but the frequency domain is easy. It's just 1 over that thing, right? If this thing is invertible, it has no zeros, and I can divide by it. But it might not be invertible, so I will divide by it wherever it is not 0, and wherever it is 0, I will just give you 0. This is the meaning of pseudo-inverse in the frequency domain, okay? So I'm just not dividing by 0. This is what pseudo-inverse does. So basically, this is my correction filter. Again, it's a digital filter. It's a translation equivariant system. It is a convolution, and its frequency response is given by this thing. So I need to compute the cross correlation of my sampling and interpolation kernels. They might be bad. They might be not non-ideal, but I compute them, and I am going to correct for their action or for lack of their compatibility by doing this digital filter, okay? And basically, you can think of it as the projection on a bi-orthonormal basis that we defined a few weeks ago, okay? Now, when are we going to have exact recovery? Exact recovery means that the sampling and the interpolation procedures are invertible. They will give us identity. So first of all, we have the sampling. It's the A to D, the analog to digital. Then we have this digital correction, which we already discovered that this is a filter. And then we have the D to A, the interpolation, the digital to analog conversion, okay, which is the synthesis operator. And we would like this H to be, first of all, invertible, and we would like the end-to-end operation to be identity. Then we say that we have exact recovery, right? So what this system produced was exactly what it sensed in the input. So first of all, if f belongs to the span of the integer translates of psi, of our sensing operator, then no information is lost when doing this projection. Otherwise, we are going to lose information. There will be some orthogonal directions that are not sensed, right? So we are going to introduce some error. Now, if we still are able to sense f perfectly from that subspace, we might not be able to interpolate it if f doesn't belong to the span of the integer translates of the interpolating kernel, right? So we might keep all the information about f, but we might be unable to express it because our D to A is not spanning the same subspace. And then, of course, if basically we have these two conditions satisfied, let's just pay attention that if phi and psi adjoint are bi-orthonormal means that this product equals identity. If they are bi-orthonormal, then we don't need correction, right? We don't need correction. And In the case of ideal Shannon sampling, we had biorthonormal analysis and synthesis, so there was no need for correction. But when did we need correction? For example, imagine the following situation, which is very typical. I'm sampling on some lattice L star, given by this matrix A star, okay? And then I'm interpolating, so let's say I'm sampling with my 12 megapixel camera in my smartphone, and then I'm displaying the image on this display. It has a different resolution, it has different number of pixels, it's a different lattice. It has different spacing between the pixels. These are completely different technologies. Sensors and displays are manufactured with completely different technologies. So basically, I'm interpolating on a different lattice. Let's say there is an integer relation, as we have seen before, between these two lattices. So there is some integer number of sensing pixels that fits into the display pixels, or the other way around. So basically, I would like to digitally upsample my digital signal. So from here, it is digital, right? Here I'm just already digital. I'm doing this digital upsampling, and then I'm doing interpolation on the other lattice, right? So we had these three operations. We are sampling on one lattice. We cannot just send that sequence, that digital image, to the display. The interpolation operation is incompatible. We need first to make it compatible by doing an operation in the digital domain. And these are the operations that we did. And then we are going to interpolate. So basically, we had this, remember, we called it resampling or decimation and interpolation, but basically, just look at what happened here. We are doing a kind of a generalized sampling. We have one basis for the sampling. We have a different basis that is not biorthonormal for the interpolation. So we need, now we have this H. This is the action of H. It is not identity anymore. It needs to correct for the basis. And if you run the math, and if you compute the inner products of these scaled sinks and the other scaled sinks by a different matrix, and you compute the inner products, compute this cross correlation sequence, and compute the system H, you are going to get exactly this. Okay, so you can view this from the perspective of generalized sampling. You have two incompatible sampling and interpolation operators, and this is the digital correction that does the work. Okay. In this case, it does the work perfectly. If you had the other situation where the interpolation would be on a lower resolution, on a sublattice of the sampling lattice, then you would lose information. And in that case, the exact recovery setting conditions would not hold, and you would be doing an orthogonal projection onto the subspace of functions that you can represent. Okay? Any questions? Okay, let's move on. So basically, we have this cool, in my opinion, this is brilliant. So it was invented by in a sequence of papers, I think in the 90s probably, or somewhere in the 90s, under the name of generalized sampling. So I think it gives a very clean and very simple algebraic picture of what we worked so hard on to obtain when we talked about lattices. And of course, it works in more complicated settings. And by the way, we can do better than just doing this least squares solution. There are other estimators that work better than just least squares. Okay, but let's step one step back and look at the following situation. So this is a 1 megapixel image. Of course, it's resampled to my screen. This is a 1 megapixel image, and I do the following operation. I will divide it into patches. I will transform each patch by an orthogonal transform, an orthogonal dictionary that is called the wavelet transform. And then I'm going to kill the low coefficients of the transform and just keep 10% of the prevailing high magnitude coefficients. And this is the image that I'm going to get. Can you see the difference? Well, maybe, so if you just look with a magnifying glass, maybe you have some texture a little bit compromised. For example, here. See, so some details are lost, but you need a really sharp eye to see the difference. This is how image compression works, by the way. You are using this kind of transform that that makes the representation sparse, and then you kill all the small coefficients, and you make it actually strictly sparse. So then the question is, so we worked very hard on building a sensor array that was able to sample this 1 megapixel pixel image, but then we threw 90% of the information, and it was practically harmless. So then why did we work so hard on collecting so many measurements in the first place when we could use just a fraction of that information? So can we manipulate the image in some way that it becomes represented in that domain in which it is compressible, in which it has this nice sparse representation, definitely not in the original domain, and then sample directly there? So of course you cannot manipulate the image in the analog world. So let's manipulate our sampling mechanism in such a way that it will sense the image directly in that compressed domain. Okay? And this is called compressed sensing. So we would like to sense the image in a domain in which it is represented in a compressed form. Okay? And this is not true only for images, it is true for many types of natural signals. As long as we have some structure, as long as we have some prior, can we actually incorporate that prior into the sensing mechanism? Okay? So let's say we start with the following prior. We have a sparse synthesis prior, and of course we can extend it to more complicated priors like the analysis priors or the structured sparsity priors that we had, and practically any prior can go, and deep learning tools can also be very useful here. So we have these sparse synthesis priors, just to start with something that is very simple. And we have this sensing operator. I will denote it by S adjoint. It computes the inner products of my function with a collection of, let's call them sensing functions SM. It's an inner product with this collection of functions. I'm assuming that I have M such functions. So basically, I'm generating an m-dimensional vector of measurements y. Maybe there is some noise also in the system. Typically, there will be some noise. But I'm not going to talk about the noise. So I have a signal that is represented by n degrees of freedom, right? So I have n coefficients representing the signal. And this, by the way, this can be done on a patch basis. This can be done on the entire image. Doesn't matter. It can be applied both levels. And I'm producing m measurements. And essentially, the signal recovery problem is an inverse problem. We would like to estimate f from the measurements y, given by this linear sensing operator. And we have a prior. It's also this sparse prior that we already know, right? And of course, we are interested in situations where the number of measurements is significantly smaller than the number of degrees of freedom required to describe the signal. So in the standard basis, a 1 megapixel image requires 1 million degrees of freedom to represent it. Every pixel has a degree of freedom. And we would like to measure less than 1 million measurements. That's the whole point. Okay? So essentially, we have an underdetermined set of measurements. Okay? So we have this set of measurements y. I can plug in the prior here. The prior was that f was given by this synthesis model phi c. So let's plug it in here. And let's now look at this operator. It is the sensing of the atoms of the synthesis dictionary, right? It will be a matrix. It will be an m by n matrix. Let's call it A. This is an sensing matrix. It's nicer to work with matrices than with general continuous operators on Hilbert spaces or infinitely dimensional operators. So basically, phi has a finite dimensional n-dimensional vector on the right. Basically, it has an m-dimensional input on the right, and it has a continuous signal output on the left, right? This is an operator that maps us from a finite dimensional Euclidean space to capital L squared. And S star does the opposite. S star maps from the continuous domain to a finite dimensional Euclidean space, an m-dimensional Euclidean space, according to the number of measurements. But now, when I compose them, I have this matrix, m by n matrix, measurement matrix. Okay? which measures directly C. And now we can use our good old map estimator. I'm not going to repeat the same mantra of how we obtain it. We, of course, all know how we obtain it. So there will be this parameter lambda that controls the amount of regularization that depends on the amount of noise we have in this measurement process. And the only thing that we now have a slightly different likelihood term, the data term. So we are synthesizing the function using phi from C, and then we are sensing it, and we are producing measurements in the space of measurements, in m-dimensional space of measurements, and then we compare it to y. Okay, and we would like to find the coefficients C that minimize this discrepancy, and then we synthesize our function using this linear decoder phi. Okay. And of course, we are plugging in this matrix A here. So now it became a finite dimensional problem. So I'm just looking at this arg minimum. Let's ignore the synthesis. This is a finite dimensional problem. It's just an optimization with matrices and vectors, right? So essentially what we have is this estimation problem. And let's ask the following question. So first of all, when can we do exact recovery? We have an underdetermined set of measurements, but we have a prior. So when can we do exact recovery? And what is the smallest amount of measurements? So basically, what is the compression ratio that we are going to get in this sensing process? We would like to, so we are going to complicate our analog hardware, maybe significantly. Can we do a better compression ratio? Can we sample it at a less dense grid? Or can we take a smaller number of measurements? Maybe there is a bandwidth advantage. Maybe we need to transmit less information. For example, if we are doing it on a satellite in deep space, this might be a very significant consideration. Okay, I will talk to you next week about how these ideas lead to what is called computational imaging, how we can do smarter types of measurements in analog hardware. And then once we discover these theoretical bounds, how to construct a sensing operator S star? How do we actually sense the image to achieve these compression ratios? So essentially, we have this problem of recovering our latent vector C. So basically, once we have C, we have F, right? So this is our unknown. This is our variable to be estimated. C is an n-dimensional vector. It has n degrees of freedom, at least it looks to have n degrees of freedom. And we have an underdetermined set of measurements. So if we just do it blindly, this system has an infinite number of solutions, right? And we are naively asking whether this map is invertible, right? So when will this map be invertible? It will be invertible if it is an approximate isometry. If it is by Lipschitz, essentially. If I take two vectors, C1 and C2, and I map, this is C1, this is C2, I map C1 to AC1, I map C2 to AC2, okay? This is basically the mapping A that it does it, our measurement matrix. What would be a disaster if two different signals map to the same point, right? That means that the map is not invertible. So I would like the distance that I measure between these two vectors not to shrink to 0, hence this left-hand side, and let's also demand that it doesn't grow too much, because otherwise this might be invertible but unstable. So I would like this by Lipschitz condition to hold with some constant delta. Okay, of course delta has to be bigger than 0 and obviously smaller than 1. This is called an approximate isometry, and obviously this doesn't hold because our matrix is rank deficient. There will be many, many vectors, an infinite number of vectors, and entire subspaces that will be mapped to the same vector of measurements y. But wait a second, we are not using the prior. Okay, we are not using the prior. We have a prior. We are assuming that C is sparse. It's not just any vector with n degrees of freedom. It has less degrees of freedom. So let's assume that our C is sparse in this literal sense, that its L0 norm is upper bounded by K. It has no more than K non-zero elements. Of course, the position of those elements to be determined, right? There is a combinatorial factor that will define the number of possible combinations. But basically selecting, think of it, selecting the support takes you roughly log of n, right? Encoding the bits where the indices are located. You need log n bits, right? N is the length of the vector. And you have k such bits to establish. So basically, the number of degrees of freedom looks like k log n, right? So you don't have n capital N. You don't have n degrees of freedom. You have k log n degrees of freedom. Log n is typically a small number, and k, if the vector is sparse, is a small number as well. So you have much less degrees of freedom than the embedding space gives you. So basically, you have a very structured input. And let's now consider this problem. We have a trivial linear algebra problem, how to solve an equation, a linear equation. But now we are saying that the vector of unknowns is structured. And it is amazing that linear algebra exists for, I don't know how, depending how you count it, for 1,000 years approximately. But only now, in the late 20th century, this problem was answered. How do you solve this structured linear system of equations? Okay. So basically, what I would like to do is to replace my approximate isometry, that of course doesn't hold for this undetermined system, by a restricted isometry. So I don't care for this A to be isometric on any vectors. I care for it to be approximately isometric for sparse vectors. Okay? So I would want this restricted isometry to hold. Okay? If this property holds, then my system is invertible. Then basically my sampling can be, I can exactly recover my signal from this sampling. Okay? And this property is called RIP. It's not rest in peace, it's a restricted isometry property. And basically we will say that a matrix A, an m by n matrix, so usually it looks like this. It's a very short matrix. It has many more columns than rows. It is RIP of order k with this constant delta k, if it satisfies this by Lipschitz relation with delta k on vectors coming from, basically on k sparse vectors. Okay, so this is called the restricted isometry property. And of course, if our matrix satisfies this restricted isometry property, if we have C1 and C2 coming from basically being k sparse, their difference will be, in the worst case, 2k sparse. So if they have non-overlapping supports, and then we can write this inequality as we demanded before, with this 2k in the delta. Okay, so we want essentially A to be to have a good delta 2k in order for be able to recover from underdetermined measurements vectors that are k sparse. Okay. So this is the restricted isometry property. And first of all, let's ask two fundamental questions here. So first of all, I'm giving you a matrix. Can you tell me whether it satisfies this property or not? It looks ugly. So it looks like you need to check all the possible supports of k sparse vectors out of n. And k out of n is a very big quantity, right? So it's this binomial coefficient, k choose n. You end up with an NP-hard problem. So it's impossible to verify whether A is RIP. So this is kind of an analytical problem, and it's unsolvable. But a more interesting question is, how do you construct a matrix that satisfies this property? So you cannot verify this property, but can you at least construct a matrix that will have this property? And surprisingly, the result is yes. And what does the job very well are random matrices. So you cannot combinatorially check the property, but you can prove it for random matrices, which is very nice. So let's say that we have a matrix A with IAD entries drawn from some distribution P with zero mean and some variance sigma squared. Okay? You can complicate this model. You can draw random vectors from some distribution, but let's keep this simple model. So we'll fix some vector C. It's a deterministic quantity. And let's see what is the norm of AC. So this is the length of how the length of C changes when it is mapped by the matrix A. Okay, so I will just write this norm no surprises. Do some manipulations on the sum. So I write this square as the product of two sums, one indexed with n, another one indexed with n prime. This is how the products open up. Okay. And now let's take the expectation of this. So of course, the only random quantity here is this orange A. And the expectation of this orange, so on purpose I assumed zero mean and IID. So zero mean IID means that these coefficients are orthogonal. So this expectation will be zero unless mn and mn prime are the same index, unless it's the same entry. So one of the sums will die. Let's kill the n prime. So I have the expectation of A squared mn, which is the sigma squared, right? So I have two sums. I take the sigma squared outside because of the IID assumption. So all the variances are the same. I have one sum here, which is just the squared L2 norm of C. And another sum just adds this factor m. Okay? So I have sigma squared m times the L2 norm of C. I will take my variance to be 1 over m. And then basically what I have is that this random matrix is an isometry in the mean. So in the mean, it preserves distances. But how well, basically, what can we do with this assumption? How tight is the spread? How concentrated is my probability of this random quantity? This is a random, this is a random quantity. How tightly it is concentrated about its mean. Okay, so basically we would like to say something about its concentration. We would like the probability of this tail. So this is my mean, right? So this is the expected value of the norm squared. It is distributed. This random quantity is distributed somehow about this mean, and I would like the probability in the tail, let's say, being more than epsilon times the this quantity. I would like the probability in the tail to be something very small. Let's say some power of epsilon. Something very small, something concentrated. So this is a concentration bound, some tail bound. And of course, we cannot make any general statement regarding any p. We need to make an assumption about p, about how the entries are distributed. And basically, it appears that this concentration holds under distributions that have strong fast decaying tails. And how did we call these fast decaying tails? We call them sub-Gaussian distributions. So basically, we would like a distribution that satisfies this kind of tail bound. We want basically very little probability to be concentrated in the tails. This is called sub-Gaussian property. Actually, the Gaussian distribution also satisfies this property with some constant C. So basically, a Gaussian matrix will do, a sub-Gaussian matrix will do, for example, a Bernoulli matrix will do with just coin tosses, zeros and ones, for example, or minus ones and ones. We need to be zero mean. Okay, so basically, these kinds of matrices will do the job. And now, so it's amazing how in mathematics, fundamental results are given a modest name lemma. So this is one of these fundamental results. It's called the Johnson-Lindenstrauss lemma. It's not the original formulation, but it is twisted to our needs. So essentially, the Johnson-Lindenstrauss lemma tells you the following. So you draw a random matrix according to the principles that I outlined. So you take it from this sub-Gaussian distribution with zero mean and variance 1 over m. So we know that the matrix will be an isometry in the mean. It will also concentrate around its mean. So the lemma tells us that if we have a k-sparse vector and you have the number of measurements essentially of the order of k log n over k, then A will satisfy the restricted isometry property with a small delta with a very high probability. Okay? So it's kind of an probably approximately correct type of statement. It doesn't hold every time, and it holds approximately, right? So, but if you allow this kind of relaxations of the exact statement, then you have a very easy recipe to construct good sensing matrices. Okay? Of course, these two constants, the one that gives you the probability of this happening and the one that tells you how many measurements you need to take, they depend on the distribution P, but they don't depend on any other parameters, just on the distribution. And for the Gaussian distribution, you will have some ugly expression that gives you no insight. But still, basically, it falls into this general recipe. Okay, so this is called the Johnson-Lindner-Strauss lemma, or the RAP property for random matrices. Actually, it is easy to prove. The original proof was horribly complicated, but there is a very beautiful proof from Rick Baranyuk's group. They published a paper about it 10 years ago about a simple proof of the Johnson-Lindner-Strauss lemma, and the proof is simple. There is some geometry, some simple geometry that you need to know, and elementary probability. Okay, so basically, back to our compressed sensing scenario, it means essentially that if we constructed this sensing matrix A, we just need an order of k log n measurements to achieve perfect reconstruction. Okay, so you do a random matrix. You know that your image is very structured in some dictionary phi. Let's say it is compressible by a factor of 100. Let's say we can reconstruct it faithfully from 1% of coefficients. So then you have a very good compression ratio, right? This log n contributes a very small factor. So you really compress your measurement process. But wait a second. What is A? A was this product of the dictionary with the sensing operator. But now we need to construct the sensing operator. How do we construct the sensing operator? So we know how to randomize this product of sensing times the dictionary, but how do we translate this into analog hardware? Analog hardware is this thing. Okay? So let's assume that S adjoint is Gaussian. So I'm a little bit sloppy here because it's not a matrix, right? It's an operator that takes continuous domain signals, but let me be sloppy. Okay, so suppose it's some continuous analog of Gaussian matrix. So we know that it will be an RIP. It will have this RIP property with very high probability if we make the ratio between the number of rows and columns good enough. Now, if phi is orthonormal, then basically taking an orthonormal transformation of a Gaussian IAD matrix will also give you a Gaussian IAD matrix, right? Gaussian distributions are invariant to orthonormal transformation. It will not color the distribution, so it will stay IAD, and hence the matrix A, the product of these two operators, will still satisfy this RIP property that we want in order to construct an efficient sampling scheme. Okay. Now, surprisingly, it also holds for more general sub-Gaussian distributions. For example, if you take binary matrices with zeros and ones, a Bernoulli matrix, for example. It also holds for sub-Gaussian matrices, and this property is called universality. So essentially, a random matrix is good for every dictionary, which is not necessarily obvious. Now, in practice, it might be difficult to implement this kind of a full Gaussian matrix or a full binary matrix. So what does it mean in analog hardware? I will show you next week how exactly you implement it in analog hardware, but you will need somehow to modulate you need to compute inner products. You need to modulate your image in the analog domain with some random pattern, with some random sequence, which might be a mess. If you have an entire image, you need to modulate the entire aperture of your camera with this random sensing function. Might be difficult to implement. What is easier to implement is sensing functions that have some structure. Surprisingly, for many types of structure, you still have RIP guarantees. And one of these structures that is very desirable is to be translation equivariant. So in particular, you can do random convolutions. You can do convolution with a random filter that is built in a particular way. So you want the Fourier transform to have, essentially, I'm oversimplifying things, but essentially to be an all-pass, to have constant magnitude and random phase. If you convolve with such a filter, then you still have RIP properties. Okay, and then of course you can complicate your sensing scheme to more interesting priors. You can have hierarchical priors. You can have analysis priors. Sometimes it is more advantageous to work with the analysis prior and not with the synthesis prior. You can also solve kind of a blind inverse problem. So suppose you don't know what dictionary is the best for your sensing. You don't know which prior to assume an image. Can you do dictionary learning together with your sensing? Can you actually learn the sensing operator? So essentially you have a composition of a forward model that does the sensing. We call it as a joint. Then you have some kind of a bottleneck here, which are your measurements, and then you have the inverse operator. Okay? Can you actually learn them together? And the answer is positive. Actually, many cool things can be done if you learn them together. I myself did some work, for example, in ultrasound doing exactly this. Also in optical imaging doing exactly this. If I have time, I will show you some of these ideas next week. Okay. So basically, this is a more modern view on sampling. I will put a disclaimer, and we'll finish here, that if you restrict the term imaging to working with this kind of devices, with smartphones, then compressed sensing is not very useful here. Because with modern CMOS technologies, it's very easy to build a 30 megapixel array. It doesn't cost you too much. So it's easy to build this. But imagine if you are doing some more exotic type of imaging. For example, you are sensing some terahertz range of images. So it's not infrared, it's the long wave end of infrared, somewhere between infrared and RF. Building pixels in this range of frequencies is very, very complicated. It's costly. So then you want the number of measuring devices to be small. But maybe it is easier to build modulators, something that will do these inner products with the sensing function. So there the ideas of compressed sensing are much more appealing than with just plain image sensors. Another domain where these ideas can be appealing, suppose you want to do more than just acquiring an RGB image. For example, you want to get actually spectroscopic measurements. You want actually to get the exact spectral content of your light, not only 3 channels, RG and B, which integrate over very wide spectral bands. Suppose you want to do what is called hyperspectral imaging, very narrow spectral bands. Doing a sensor that does this in CMOS is a very complicated task. And there you can do very interesting, crazy optics that will do compressed sensing with a regular sensor. So you do some crazy optical system that is then sensed by a regular CMOS sensor, by a regular square array of pixels. And you can do many more interesting things. I will show you some of these crazy designs, including a camera that has just 1 pixel. So this is next week. Thanks.